Welcome. And I'm very proud and pleased to welcome Dr. Lila Chrysikou, somebody who I've known, I guess, I don't know if since you were a postdoc or maybe shortly thereafter, who does really wonderful work on concepts on cognitive reserve and creativity and regulation. She is an associate professor in the Department of Psychological and Brain Sciences at Drexel, and she's the director of the Applied Cognitive and Brain Sciences PhD program and associate dean for research in the College of Arts and Sciences. She's also the co-leader of a new Bachelor's of Neuroscience major at Drexel. And she has a PhD in Brain and Cognitive Sciences from Temple. And she has background in imaging, and as well as doing work with a lot of behavioral work, fMRI, TECS, to study creative thinking and problem solving. And she's authored over 60 articles and book chapters and is a very accomplished person in her field. And so we're really delighted to hear from her today. So let's give her a welcome. Thank you.
Laura, do you want to go over I think there's some logistical slides in the beginning for those who are doing the continuing education. So I'll put that on the screen. Thank you so much, Laura, for the introduction, and thank you for inviting me and having me here. Put my timer on. I've actually never been to this building, although as a postdoc, I was actually an employee in Myrna Schwartz's lab for about a year. But somehow I made it, never physically in the building. But I've been a very big fan of this series, and I'm truly honored to be one of the invitees, as I've been a member of the audience many times. As Laurel mentioned, my lab is at Drexel. I've been there for about 7 years now. Before that, I was at the University of Kansas for a little while after I finished my postdoc at Penn. Our work over the past several years that I'm very excited about is on a topic that's exemplified by this figure. So on a couple of weeks ago, on May 27th, I flew from Philadelphia to Barcelona for the APS conference. And in the transatlantic flight, in the bathroom, I noticed there was an unusual smell. And then I noticed that there was this kind of contraption here, which is a duct tape coffee pod, the ones that they use on the planes for speed. So these are designed so that, like the hotel ones, so you throw them in hot water and they make very strong coffee that tastes a little interesting when you're on the plane. This was used as a space freshener, an air freshener. So they duct taped it. It was working beautifully, but I rushed and got my phone because I like to show examples like this in my talks, because this is precisely the kind of process that I'm interested in, how people use objects in these different ways, and to achieve different goals. And I'll show you just a couple of other examples. This is from a bathroom on I-70. So the highlighter was the perfect fit to fix this problem of the broken faucet. And this is from a student in one of my classes back in the day. As a graduate student, I was teaching at the community college here in Philly, and one of my students submitted their final paper with a hair clip instead of a paper clip. And it was an abnormal psychology class, so I couldn't give them extra credit. It was not an activity class, but I've been since told that this was not fair on my part. We understand, of course, that necessity is the mother of invention, but my questions around this particular type of object use are about conceptual knowledge. And more particularly, my lab is studying what I'll broadly define as cognitive and affective regulation. Focusing, though, a little bit more particularly on how we use semantic peak memory and executive function in the service of everyday problem solving and creative thinking. So there is a range in terms of how good people are in these types of tasks, but all of us have done this before, and we are really good when the situation presents itself and how we are kind of transforming and flexibly using our conceptual knowledge in the service of particular types of potentially impromptu goals we have never faced before. And more recently, although these are questions that have been lingering in the background, a lot of our work is trying to find ways to connect what we're studying in the laboratory with what happens in the real world, particularly when it comes to design, of any type of either physical object or any aspect of design, design of our world, if you will, because this is sort of a very signature activity of who we are as human beings. So we were very interested in real world applications as much as possible. So, so the central question that my lab has been trying to figure out is what are the cognitive and neural mechanisms that allow us to use this conceptual knowledge that we have flexibly to generate new ideas or generate new artifacts. All of the things, if you look around you, have been generated by humans. But where do these ideas come from, and how we're using the things that we know, particularly to create ideas and artifacts that do not exist, have not existed before. And in this conversation, I will define concepts as dynamic tools in the service of adaptive behavior. And I don't get to give talks to an audience like this as frequently, so I typically talk to the neuroscience creativity crowd a little bit more. So I'm very interested in your input and feedback from your perspective, studying populations who may have a different type of variability and challenges in that regard. So two key ideas I will highlight in this talk is that I consider the process of being successful in coming up with these new ideas as a combination of the process of conceptualization or meaning making and the process of regulation or cognitive control. And none of these ideas should be particularly novel, but in the context of the particular tasks we are discussing here, we are trying to figure out how these two processes combine and to what extent we can predict the outcome, if you will. So a little bit outline of the talk. So I will try to give a brief background on kind of my take on conceptual knowledge in this context, and then I'll talk a little bit more about some of our studies in the lab that focus on conceptual knowledge in the service of creative problem solving from various methodologies. And then, depending on our time, I'll touch upon some newer work on emotion concepts and kind of the other side of flexibility, fixation, and rigidity, and hopefully reach a couple of conclusions at the end. So in terms of a little background, and I'll try to keep this a little bit short. So traditionally, of course, we have been familiar as cognitive neuroscientists with takes on the organization of semantic knowledge as category specific. So it's organized in these taxonomic categories: mammals, birds, vehicles, and so forth. And this has been a helpful way to get the research on concepts started. There have been some variations of these perspectives over the years, very influential approaches, and to an extent, of course, they do hold true. But the model that I had found many years ago is particularly influential in how I'm thinking about the processes that support that type of meaning making in real world object use. Are a little bit more aligned with this distributed representation approach to semantic cognition, according to which that knowledge is organized according to the domains that have originally participated in the generation of this knowledge. And this is from an old paper from a variation of an Albert paper that Sharon Thompson Schill and colleagues had provided, where this was meant to be the telephone, right? So this is an object that is, I guess I can't use the pointer on the laser. That's always the trick with these screens. So the object concept that has tactile features, action features, visual features, and the like. So This second modification or approach to this question of distributed representations also came from the work of Larry Barsalou. I found his work very influential in my thinking of a flexible object use, as his take was that the process of conceptualization and categorization is the process of essentially a construction of a temporary working memory representation of a concept on a particular occasion and within a particular context. So a concept in this regard is this temporary construction that's used to represent a particular flavor of a category within a specific occasion. So this idea of ad hoc conceptualization is also very relevant and influential in thinking about day-to-day object use, flexible object use. And last but not least, I was in the audience when Ludwig Desai gave his talk last week, and he presented extensively his take on the distributed hub and spoke model, and that has been also a very formal way to think about the organization of knowledge in a way that brings together these different categories. So that's the more traditional version of the model, and the idea is, of course, that these attribute-specific parts of categorization are brought together in this modality invariant hub in the anterior temporal lobe. So there is a way through which these theories have provided some ideas as to how we can have object representations highlighting different aspects of semantic information, and that information is essentially brought together in an unmodeled way potentially, although that again may mean different things. Part of that particular group has also suggested in more recent views, and briefly mentioning the contributions of the prefrontal cortical systems, and their semantic control approach suggests that the way through which in a real world context we are tapping on these different pieces of semantic memory may be guided by particularly left inferior frontal cortical systems. Now, I do agree to an extent with these views, that what had got us thinking about this particular model in the context of the tasks and questions that we have is what's defined as these executively demanding semantic processing that's presumably taking place in these prefrontal systems. So a lot of our thinking was about what this executive demanding semantic processing might entail. A lot of the tasks that have been used in this research in creating these models typically involve retrieval, where there is a right answer, the participant is, or the patient is asked to come up with the right answer, and when the competition is higher, or where the task is more executively demanding in that regard, or there is weak associations in semantic memory, that's where that contribution of the semantic control regions and prefrontal systems is kicking in. And we started thinking about these mechanisms, but in the context of the type of tasks we are interested in. And I will define those tasks as open-ended, where there is no right answer. So you really need to fix the fact that you don't have an air freshener in the bathroom of the airplane, or your faucet is broken. So there is not necessarily a right answer. You can't just retrieve that information from semantic memory. So our question was whether these are the same systems that support this flexible dynamic recategorization of a highlighter as a part that can fix the faucet, for example, or a hair clip as a paper clip. And if we make this a little bit more concrete, we can think about mapping the hair clip by the distributed model of semantic memory. So this is a type of object that has ridges, is long, can melt, is gray, is made of metal, of course has a very particular function, holding hair up. And so these are all properties of this particular object in memory. But the question is, how do we make one of them a little bit more salient than the others in the context of a very particular goal. In our tasks, we don't ask the participant, what do you use the hair clip for? They have to come up with that connection, if you will. And so our question is whether the models of semantic organization and semantic control are allowing us to understand these processes in the same way that it has been for these more traditional tasks. And I will note that in the real world, in these context-specific situations, for the participant, this is not a surprise, right? So the fact that the hair clip can be used as a paper clip because of that shape and the way that it can bend to serve this purpose is it was immediately obvious to my student, at least, but also in the traditional use of the object is not like the person is trying to suppress actively that, for example, the hair clip, the paper clip, or the hair clip can melt, right? So it's not that aspect of the object representation is not something that is in need or emerges in every single situation. So some aspects of that representation are more salient than others in this context. So, so we're very interested in how people construct these representations actively as they try to solve problem in the real world. Now, a little bit outside of the semantic control idea, a lot of the discussions about focusing on salient aspects of object representation are situated within a lot of the theories of prefrontal cortical function. So this is the region, especially in the left prefrontal cortex, and more particularly the left inferior frontal regions, especially pars triangularis and area 45 or 47 here. Oops, I think I did something wrong here. Sorry. I'll just, so these are the areas that have been traditionally suggested as providing this top-down regulatory guidance. And so they promote salience of bottom-up processing. They're quieting down the information that is not relevant while bringing into the forefront the information that is relevant. And so there's a kind of an extensive body of research that has supported this idea. But part of our question was whether this is capturing all of these flexible thinking situations. A lot of the literature in some aspects of cognitive regulation, particularly within the developmental literature, but also some of the animal literature and some of the learning literature, has suggested that under very particular circumstances, exerting top-down regulation may not really be good for everything. So aspects of learning, if we think about language learning, for example, or probability matching, exerting top-down regulation is not going to optimize performance. So there are these interesting paradoxical cases according to which exerting top-down control by the contributions of the prefrontal cortex may not be a good thing. And so, but being hypofrontal might be beneficial for learning or aspects of cognitive flexibility. So we put together this idea at the same time. Sébastien Hellier, who is currently a professor at Purdue University, he had proposed a computational model that was also very much in the same spirit, suggesting that problem solving in the real world and regulation in the real world might be this iterative play between explicit or rule-based thinking and implicit or associative processing. And during testing, coming up with ideas, testing these ideas, there's these micro iterations that are happening and they unfold while the participant is trying to solve a problem and until that problem is satisfactorily approached. And so that computation model had very much the same flavor, although it didn't explicitly reference the brain. And a few years later, we put together this more organized based on some of our data and others, this more organized framework, which we called the matched filtered hypothesis for cognitive control, that essentially suggested that the application of regulation, at least on the cognitive side, is an interaction between what are the task requirements in terms of abstraction and what the organism requires in terms of whether low filtering or high filtering is required. So, for example, there are tasks, working memory tasks that can benefit from prefrontal cortical systems being engaged because these tasks fall within the parameters of working memory, and that performance is guided by that higher level of abstraction required in the task. But then there are other tasks that, for example, exceed the capacity of working memory. Think of a learning task or a weather prediction task. These are not tasks that can be memorized, if you will, or benefit from high abstraction, and therefore more posterior subcortical systems might be the ones that are optimizing performance. So it's not that cognitive regulation is one size fits all. You should apply it every single situation to everything, but rather there is a much more nuanced approach to how we are thinking about the application of that regulation, at least as far as the task parameters can be laid out. And that in fact, these two systems might be on occasion competing with each other. So these competing interactions might result in these behavioral, at least trade-offs that we see in terms of performance in certain tasks, where application of cognitive control might be bad for some things, but toning it down may actually improve performance. So with that very brief background in mind, we set off to see whether some of these ideas could be tested in the lab and how concepts can be constructed flexibly in the context of everyday problem solving. I will say that in terms of within the more particular subfield of the emerging field of creativity science or creativity neuroscience, a lot of these ideas have been embraced in the formation of a model about how people are creative or solve problems creatively that suggests that both spontaneous thinking and controlled thinking are critical for flexible creative problem solving, and that type of thought requires the generation of unexpected associations, but also the ability to evaluate whether these ideas work in context. So, for example, coming up with thinking about whether the coffee pod is a good solution to the problem of the bathroom, but at which point do you evaluate that, this is a good idea, I'm going to try it out and see how it works, right? So you came up with possible solutions, but at which point are you evaluating and in fact implementing these solutions? And again, all of us have done this. So you can reference a similar situation from your own life in the same way. So this idea has been proposed in these models of creative cognition. So us and others have suggested, and there is now probably about a decade or so of extensive data, multiple studies that have supported this idea, that we have these two different large-scale brain systems, the executive control network system and the default mode system, that are working in parallel or in different phases of the creative process. And I'm using this seesaw metaphor, visual metaphor, to suggest that sometimes for some aspects of these tasks, the idea is that the generative phase benefits from more default mode activity, whereas the evaluation and execution phase benefits more from the executive control network activity. And of course, the big question is what determines the balance? Are there individual differences? Are people who are better at these tasks better at modulating where they switch from the one mode to the other? Is it true that there are these types of modes? There is, again, sufficient evidence to suggest that in these separate phases, we have been capturing activity in these particular networks when someone is generating or someone is evaluating these ideas. But what performs the switch? One idea is that the salience network, regions within the salience network, are the ones that are determining whether one is going from the generative to the evaluative phase and so forth. But this an idea that has not been tested as extensively just yet, but that is a key a piece of the model. So a lot of the experimentation, of course, aside from providing evidence for the model, has to do with what happens if we try to manipulate the systems. Boosting the default mode network activity, would that create more cognitive flexibility in problem-solving tasks, or quieting down the prefrontal cortex, would that come up with support participants coming up with more ideas, if you will? So I'll share with you some of the studies that have provided some support from our lab, but also a lot of open questions. So we set off to first establish in an exploratory study that this is what we see. If I were to put each one of you in a brain imaging scanner for a functional imaging study, and I were to ask you to come up with an uncommon use for a bottle or a ladle or a belt, what would be happening in your brain during that generative phase. What we have established is that, yes, indeed, when you are coming up with these uncommon ideas for the objects, there is significantly less prefrontal cortical activity, but more posterior visual cortex activity in particular. And if we are showing you the common use for the object, so you're showing a ladle, you're saying to stir food, the left prefrontal systems, the ones that we have seen in multiple semantic retrieval studies, are the ones that are activated in that context. And in fact, in that study, we have seen that if we classify what the type of responses participants came up with, more specifically, whether the responses suggest that the participant was breaking down the object into its basic components. Like, for example, for the wooden spoon, the ladle, burning it to use as firewood, right? So the more participants came up with ideas that completely disintegrated the traditional or semantically typical use for the object taxonomically, the higher the activity in their visual cortex. So that's preliminary in the context of a small sample in this exploratory study. Now, some of these ideas have been replicated by others. There are some data that are essentially showing very similar results from Heath Matheson and colleagues using a similar version of the task. Now, many years later, we followed up on this study because it's only capturing the generative aspect. So we've established that, yes, potentially lower prefrontal cortical activity might be helpful for coming up with these more salient, property-based aspects of object representation, but we didn't really capture as much about the evaluation aspect. So this is a project that was led by Yoed Kennett, while he was at the University of Pennsylvania in collaboration with Danny Bassett and Sharon Thompson-Schill, used the exact same task that we used, but used a network neuroscience approach in a fairly complex two-session design where the participants came in the lab, they did the generation aspect of the task, and then we recorded their responses, and then we created person-specific testing scripts when they came back in the lab for a second scan about a week later, where they were shown their own ideas and ideas generated by other people, and they were asked to evaluate how good their ideas were. So the person was essentially not in the same. The ideal case would be to do this online, but of course this is very challenging. So with that time separation, the participant was seeing their own ideas and evaluating their ideas as well. So this is the first study that tried to capture both the generation and the evaluation aspect in the same context. And what Yoa did was to use these three network neuroscience measures, neural reconfiguration, integration, and recruitment, to capture how large-scale brain systems might be collaborating in these different aspects of thinking about these objects in a flexible way, but also evaluating the effectiveness of these ideas later on. And I'll highlight that neural reconfiguration is capturing how these brain regions are dynamically changing which group they belong to or their functional community across the duration of the task. Neural integration is reflecting how these brain regions from a particular system are functionally integrated with other systems. And then the neural recruitment is kind of more general measure that captures how these brain regions are connected with each other and other neural systems across the brain. And what we found in this project was that reconfiguration, but only within the default and salience mode networks, characterizes the process of idea generation, but not evaluation. And in evaluation, only system integration was the measure that captured the neural activity, but that was unrelated to whether someone was evaluating a particular creative task or a control task. So it was a much more general evaluation mechanism. And in fact, there is specificity such that the executive control network was the one that was possibly unsurprisingly involved in this idea. But these were the first evidence in a way that has not been captured before that provided support with this idea of flexible object use, but in the context of the entire brain and the combination of the tasks. Now, naturally, we moved on to test some of these ideas with non-invasive brain stimulation. So we tried a few studies that attempted to capture how the brain potentially may be possible to be modulated in reducing prefrontal cortical activity, and whether participants would come up with these flexible ideas that are focusing on object properties that are not the typical ones in a faster or better way. To do this, in my lab, we use different forms of transcranial electrical stimulation. I know some folks here are familiar with these approaches or are using them. Very briefly, in conventional transcranial electrical stimulation, we are applying very small amounts of electricity, equivalent to a 9-volt battery, over particular brain regions, and we make the cells in the underlying brain region either more or less likely to fire. So the cells don't necessarily fire like they do with TMS, for example, but they become the state of the system is modulated to an extent, if you will. And conventionally, a nodal stimulation is thought to increase the chances that the cell will fire, and cathodal stimulation decrease the chances that the cells will fire. So in a preliminary study, we leveraged this approach to answer the question, what would happen in the types of responses people are generating when we show them objects and we ask them to come up with uncommon uses for them. And so in these studies, we stimulated with conventional DCS at first the left prefrontal cortex. So we used cathodal stimulation over roughly the left inferior frontal gyrus. These are 5 by 5 centimeter electrodes, so it's a pretty large region. But what we're showing here in the models is that the electrical field models is that this is a relatively focused area that we are influencing with the stimulation. And the task is the same that I was showing you before. Participants are either looking at objects, pictures of objects, and they're coming up with a common use for the object, or they're coming up with an uncommon use for the object. And on the left, these are the results of our original experiment with a modest number of participants, about 40 or so, where we showed that only in the condition where we toned down, reduced activity in the left inferior frontal cortex, participants became faster in coming up with the uncommon uses for the objects, but not the common uses. And they also came up with more of these ideas. So something about how the properties of these objects are thought about was modulated by reducing activity in prefrontal cortex, as we would hypothesize based on our theoretical framework. Now, this was just a single study. An issue with electrical stimulation studies is that across laboratories, there is a lot of variability in devices, size of the electrodes, the participants, how strong the stimulation is, and so forth. So what we attempted to do, we had a very large group of studies where we tried with the exact same experimental parameters, this manipulation to ensure that we are getting the findings, we're replicating ourselves, and we're not getting the sort of noise that we would be getting if we were to combine studies from different laboratories with different stimulation parameters. So across over 240 participants, only the condition where the participants received inhibitor stimulation over the left frontal cortex is the one that facilitated faster responses and less omissions in this particular task. So when participants were coming up with uncommon uses, but not common uses, and not any of the other conditions. Now, we also started using there's a handful of studies that suggested that one can capture prefrontal cortical activity at the alpha kind of oscillation in prefrontal systems that has been correlated with flexible cognition. There's a handful of experiments. This is work by my recently graduated master's student, AJ Yilmaz, and AJ wanted to have an experiment where she's testing what would happen if we force the brain to oscillate at that a optimal frequency for flexible object use oscillation at 10 hertz. And so that's what she did. She also did 40 hertz in prefrontal cortex and sham stimulation. And what she found using the same task and a control arithmetic task was that participants only in the 10 hertz condition improved the originality of their responses, scored both by human participants, but also by a large language model-based AI in terms of their performance. And that was only for the 10 hertz condition over the frontal cortex, but not the 40 hertz or the sham. And that was not something that we've observed in the arithmetic task. So we have a follow-up experiment that is testing other aspects of the frontal parietal regulatory system, specifically these oscillations over parietal cortex. But this is an experiment that we have just started, so we do not know much about that yet. So you may have been thinking, okay, sure, this is a good task. It's a different task, but it's not really representative of exactly what I talked about in the beginning of the talk. If you've noticed, so this task that has been used extensively in this literature and is considered one of the key measures of flexible cognition, it's not really a task that's representing how we do this in real life. So we don't just walk around looking at objects and think about what we could do with them. In fact, we kind of do the opposite of that, right? So we have a problem, and then that problem is the one that is guiding how we go about the search of features in memory that perhaps may be used to satisfy the goal we have in front of us. So one of the concerns is whether we are in fact capturing these processes in the best possible way, and how we can move some of these tasks from the laboratory to a little bit approximating what happens in the real world. So we kind of did that in terms of flipping the task around. So instead of using the traditional alternative uses task, we came up with the alternative objects task, which essentially shows participants the goal, sort of what happens in real life. I need to fix the faucet. I need to hand my final paper and I don't have a stapler. You start with a goal, and then you ask the participants to come up either with the most typical object they can think about that can satisfy this goal, which arguably can be a sort of a semantic retrieval task, right? So what do you use to write? You use a pen. But also, if you are to be in a situation where you can't find a typical object to use, what is the most uncommon thing you could possibly use to write? Right? So that's the task. So the participants see the goal, and they have a few seconds to come up with either a typical or an atypical object that can satisfy this goal. Some examples here: to use to flatten dough. Anyone? An atypical object to flatten dough? Good. So it can work. So we would score your response, right? And then relative to you, how many people came up with this idea. Sure, tie someone up. A little harder. So there's variability in these responses. So we have about 75 of those, and participants are doing this task in the lab. And we collected brain imaging data and brain stimulation data. So these were experiments that were unfortunately interrupted by COVID, and we still haven't. We're in the process of finishing up data collection. So very briefly, what we found on the imaging side is that we do see prefrontal cortical involvement for both conditions, but also left posterior parietal involvement from the uncommon condition. So what you just did when you came up with the uncommon object, that was the region that distinguished the performance from the common use task was in the left, left posterior parietal cortex. So left is left, right is right here. So this was only for the uncommon condition relative to the common condition. So it was left inferior parietal lobule. So based on this, the imaging data, I don't have the exact parameters. What were you thinking? I believe it was closer to IPS, or
Is it close? A lot of work now being done with SMG as supramarginal gyrus as a region that sort of holds and stores different action candidates and buffers them for the purpose of selection.
I don't think this right. It's a good. That's a good point. We may need to reanalyze these data anyway, but we haven't seen the SMG.
Yeah, since he ran this. Well, no, this is a recent study.
It's a recent-ish study, so we might want to reanalyze. That's a good point. Yes, but we hadn't seen this in prior studies. We did see the prefrontal involvement, which we sort of were expecting, but it's a little different. So the task has a goal now. It's not just coming up with ideas, right? So in the real world, it actually has a goal, what you would do in real life. So once the goal is there, then maybe high prefrontal activity might impact originality, we were thinking, but it may not have had the same consequences when it comes to number of responses. So we saw we run a high definition transcranial direct current stimulation study. So this is with about 90 participants, and we sort of replicate that effect. But so there was a significant interaction for the voice onset reaction times. It's not significant for the omissions, where when the participant is receiving anodal stimulation, inhibitory stimulation, we see that sort of facilitatory effect. But we don't really see that for uncommon shaman, but the results are not as clean as in our other experiment. But this is still an ongoing study. But we do see that the subjective novelty of the responses was higher when we inhibited the activity in the left prefrontal cortex with a high definition. So we replicate, but also a slightly different result now that the goal is there. So we think this is a better task in terms of mapping the goal with how we are approaching the aspects of the object that are being highlighted. So overall, across these experiments, we did find some support for the matched filter hypothesis and sort of versions of that within the creative cognition approaches, but we still have a lot of open questions about the timing. So with the methodologies we're using, we don't really have good information on that, quick, possibly within millisecond iterations of these processes that might be taking place while you're entertaining these ideas. So these are not methods that have allowed us for capturing that accurately. We don't have as much, we don't have as clear of a picture in terms of connectivity, aside from the evaluation study, generation evaluation study with you and Kendit that I mentioned earlier. And we still have a lot of questions about individual differences in how these neural dynamics are affected by this process. And how do these data inform how we're thinking about the semantic system? We didn't see any anterior temporal lobe activity in these studies. We haven't manipulated that actively. But how do they inform how we're thinking about the organization of semantic knowledge? We started thinking about properties. So a lot of our tasks are sort of broader in our attempt to capture real-world cognition. They're more broad problem-solving tasks, but they don't really capture these different aspects of object properties. And so in a series of studies, and this is work with a fantastic undergraduate I had in the lab a few years ago, Gavin Hansen, where we try to create this mapping of the goal and the task in a more particular way, a more precise way, if you will. And so this task presents the participants with a goal, and the subject is then looking at an object. So the goal is to illuminate, the screen goes away, then you see a candle, and then you see two other objects that potentially the first object is matching with, but only in the context of a goal. So your task is to say which object, the hammer or the flashlight, matches the candle in the context of illuminating. Yes? Does that make sense? Yeah. So again, our idea was to capture what happens when you say, how is it that you're coming up with the idea and saying, oh, this hair clip can be used as a paper clip? How is it that you're performing this matching, that these two things could be doing the same thing in this particular situation? So one set of trials was the typical mapping, and a different set of trials was the atypical mapping. So the target and the object are matched, but in an atypical way. So to burn, you see newspaper, and then you have to match whether pen or pencil fit with the newspaper in the context of this goal, right? So you can't burn the pen, so the pencil and the newspaper kind of go together in this context. But these are distractors as well, right? So, we did a lot of work in trying to create this stimuli in a way that this works in this particular fashion. And this was a brain imaging study. And what we found was that the regions that were differentially recruited when this goal target association was atypical are both in prefrontal. So this left is right and right is left for these are prefrontal regions, but also this left posterior parietal regions that I've mentioned before. And there is a typicality effect. What you see on the top panel is that the more atypical is the association between the goal and the object, the more you see activity in these highlighted regions, but then the more we also measured suitability. Is this object suitable for this goal? And what we found was that there are more posterior, more visual regions that showed this effect of suitability. And then we had a follow-up experiment trying to figure out a little bit more this role of the IPS that emerged in this study. So for this one, and I will only mention the results very briefly, but we can discuss more. So this is a paper we had out a couple of years ago, where we essentially showed that the IPS, this was the results of a searchlight multivariate analysis in a task that asked participants to essentially perform a version of this task, but pair based on property, either specific concrete properties, so match these targets based on color or shape or theme or function. And what we basically found in this study was that the IPS was the region that was sensitive to distinctions in attention within both concrete and abstract properties, but not these higher thematic categorical properties across the four-way classification. And we can talk more if someone has questions about this. We didn't have, this was a whole brain analysis, so we have a follow-up, a high definition fMRI experiment with very nice data that is focusing on the IPS in hopes of disentangling with a more precision task and an event-related design, precisely what that means for the role of the APS and focusing on particular object properties in the context of these goal typicality types of performance. Now, I think we are very close to be on time, so let me wrap up quickly here and share with you. I'll skip the emotion concepts. I will only mention very briefly that this type of flexibility we have found also holds for not just for concrete object concepts that I've been discussing today primarily, but also the construction of emotion concepts also relies on similar types of processes, and happy to discuss this afterward. But I will conclude with noting briefly that focusing on different aspects of the object representation, as we've discussed so far, can be positive, but there's also certain circumstances where some aspects, like visual features in particular of the object representation, might be problematic. we have shown, both in more traditional laboratory studies, but also in more real-world problem-solving design tasks, that once we ask participants to come up with uncommon uses for objects, and we show them pictures of these objects, their responses tend to be less flexible and focus are closer to the typical use as opposed to the atypical use. So we have a series of behavioral experiments that are showing that. There's also a line of work within design problem solving that highlights this aspect in a more educationally relevant way, namely this idea of design fixation. Once you try to teach someone, especially within an engineering task, how to solve a design problem, once you show them a picture, they are much more likely to replicate that picture in their design problem solving approach, as opposed to come up with a novel idea that will approach the problem in a more effective way. And what we're trying to do is disentangle, both behaviorally and neurally, what are the parameters that make the visual aspect of the object representation closer related to the typical use, what sort of highlights and underlies these replication effects in this context. So in short, the stimulus, the way you're presenting your stimulus may matter. So that's a larger study we have underway that tries to do that, combining brain imaging and design tasks like that with other many behavioral individual differences measures. So what I've argued today is that concepts are not simply stored or retrieved or just simply passively activated, but they're continuously constructed and reconstructed to support adaptation in a dynamic and ever-changing world. I also shared with you results that frontoparietal systems might support that flexible deployment of conceptual knowledge by maintaining goals, directing attention above and beyond the physical world, but also directing attention in memory with regards to these different properties and evaluating different interpretations. And last but not least, that conceptual processing is shaped by context. The modality in which information is being presented, whether it is visual or pictorial, whether it is verbal, may affect the ways through which that knowledge is being retrieved, especially in these real-world problem-solving situations. So with that, thank you all for your attention, and of course, thank our team and our sponsors for a lot of this work.